Okay, so let me start by thanking the organizers for the kind invitation to come here to CIRM. It's a pleasure to be at this place, and well, when I was approached by you, this conference on the memory of Georgie, it was clear to me that I should speak on our only joint project, which was completed in the last couple of years. So this is of course joined also with other colleagues, with Pavel Exner and Vladimir Lotorajczyk, who is among us from Prague, Markus Holzmann from my group, and yeah, last but not least, Georgie was joining this project here. Okay, well, I like this conference poster very much. So it's really a beautiful drawing. And so what is this talk about? You can find this talk actually here. With a little small change, this compactly supported or short-range potential should probably be replaced by a distribution. Yeah? But apart from that, most is here. Good. And before we go to mathematics, let me tell you where this comes from. So it was a couple of years ago when we got interested in singular perturbations of the Landau Hamiltonian. By we, I mean Pavel Exner, Markus Holzmann, and Vladimir Lotorajczyk. And well, it didn't take long. I had some exchange with Georgie on this topic. He then invited me to Santiago and we discussed. Georgie was visiting Graz and we met on conferences in Europe. This was around 2018, 2019, and that's when our collaboration started. And it was actually Georgie who somehow posed the right questions and asked for the fate of Landau levels under singular perturbations and other things. And so it didn't take long. In 2019, I think we already had a first draft of our, unfortunately, only joint paper, which was then completed in 21 and published posthumously in 22. What I want to show you is at least one, probably, of the last notes by Georgie on our joint project. So I'm most grateful to Lilia Simeonova, who provided us all these handwritten notes. So there were many pages by Georgie. This one you see was in February 21. And there were many pages, trust me. And so even after very tedious computations, you see, he still seemed to be in good mood. So Georgie, I think, was not only an exceptional mathematician, but he was a tough guy, and he was a great collaboration partner and friend, and a man of good humor. So he will be missed. Okay. Let me come to the contents of this talk. It consists of 3 parts. As a warm-up, I want to familiarize you with singular potentials or point interactions. Then we approach the main object in this talk, which is the Landau Hamiltonian with the delta potential. And the results actually will be in the 3rd part, spectral theory for such Landau Hamiltonians. Good. So maybe not everybody is familiar with singular interactions, and this is a kind of brief introduction how one can approach these type of distributional potentials. So we start basically with the simplest case you can imagine, which is a delta point interaction for the one-dimensional Laplacian, where your distribution delta is just supported at a fixed point y on the real line. So the idea is to give a rigorous meaning to this type of differential expression. And one way to do it is via transmission conditions in the operator domain. So the point here is the action of the operator itself is just standard second derivative, Laplacian without anything exceptional. But then something is happening in the domain, which is kind of unusual. So away from this point y, where the distribution is supported, everything is as usual. Yeah? Functions are assumed to be Sobolev H2 regular. But at the point y, you have transmission conditions. There is continuity of the functions in the operator domain, but the derivative has a jump, which is proportional to the value of the function with the factor alpha, which kind of measures the strength of this distribution. Yeah? So a delta interaction here is kind of embedded in the operator domain, and you do not see it in the action of the operator. So what does one know about this type of Schrödinger operator? Well, you first check it's a self-adjoint operator in physical Hilbert space L2, unbounded, of course. Well, if the alpha is 0, so then formally, of course, this distribution is absent. Well, if the alpha is 0, you see the second condition reduces to continuity of the derivative. Then you end up with the usual Laplacian, where it's clear the spectrum is a positive half-line, just by a Fourier transform. Well, and if the alpha is non-zero, you can view this as a perturbation of your unperturbed or free Laplacian. And because you just change boundary conditions at one point, this is rank 1 perturbation. Rank 1 in resolvent sense, to be more precise. And that has not much effect on the spectrum, except that, well, an eigenvalue may appear, which you just compute is minus alpha squared over 4, in the case that your coefficient alpha is negative. For alpha non-negative, there is no additional point spectrum. And of course, essential spectrum is preserved under rank 1 perturbation. Well, you could also approach this operator from a different angle using quadratic forms, in which case you do a form-bounded perturbation by this boundary term here. And so this operator is the same as you would associate to this closed semi-bounded form defined on the Sobolev space H1. So these are two different ways how you may define operators with delta interactions, but you still may wonder, why is this the right type of definition? In which way does actually the form or the definition up here fit with what a delta interaction should do? So here's something like a, let's say, heuristic physical argument or proof for it. So if you would have an eigenfunction, psi, corresponding to an eigenvalue E, respective to this delta potential, and you would integrate this equality, which I've done here, just in the neighborhood of the point y, where the distribution is supported, then you could continue computing here, and taking the antiderivative of minus double prime gives you psi prime, evaluated at y plus epsilon and y minus epsilon. Of course, the action of the delta distribution should give you the value of the function at that particular point. On the right-hand side, nothing has happened. And if you now assume continuity of psi and you send epsilon to 0, then the right-hand side should vanish, and the left-hand side actually would tend to this transmission condition that you see in the operator domain up here. So this is a kind of hand-waving argument. Why actually this operator domain, why this operator domain here or this transmission condition is the right choice. So here's the second argument. The second argument is via approximation. So if a delta distribution is a function which is infinite at the point y and 0 otherwise, one may approximate the distribution by a family of locally scaled potentials, with supports shrinking and values increasing. And if you do it in the right way, this is not completely precise here, then actually also the corresponding operators converge. So our operator with delta interaction supported at y can be viewed as a limit of standard Schrödinger operators with a family of potentials that basically shrink at the point y with values going to infinity. You have to do it in the right way. This limit is in the norm resolvent sense, so it's safe, let's say, for spectral analysis. Okay, so delta point interactions arose in the physics literature almost 100 years ago, but it was only in 1961 that they were given rigorous meaning as a mathematical literature. This is a paper by Berezin and Fadeev that I'm quoting here. Well, if you really want to have literature on point interactions, I think the standard reference is the monograph by Albeverio, Gestesi, Höckron, and Holden. And there is another monograph which I would recommend to look at. This is the book by Albeverio and Kurasov, published in 2000. And well, then there is almost infinitely many contributors and papers on delta point interactions. So there is a lot of literature in the mathematical world scattered around on such type of questions. Yeah? Anyway, so I'm not focusing here on point interactions, but I want to go beyond, which was already indicated in the very beginning. And this beyond goes in various directions. So first of all, instead of the one-dimensional Laplacian, I would replace this one by the two-dimensional Landau Hamiltonian. So you see here the magnetic gradient, and the vector potential is generated in this way. B, the strength of the magnetic field, is just some constant positive number. So this is Landau. Next we perturb, but not by a point interaction, but I would like to perturb with the potential or with the distributional interaction which is supported on a closed compact curve in the two-dimensional plane. Third issue, which is not such an essential generalization, but we have it. Well, instead of a real valued coefficient alpha in front of the distribution at the point interaction, we can here allow L infinity functions, so variable interaction strengths, if you wish. Real to keep the whole thing self-adjoint, roughly speaking. So, in short, I would like to do spectral analysis for a magnetic Schrödinger operator of this form. So once again, here is the Landau Hamiltonian, and we perturb it by a distribution supported on a curve in the plane. Well, then first you need to, of course, ensure that this is a self-adjoint operator. Afterwards, we will be interested in its spectral properties. And as a justification of all this, I would like to present you an appropriate approximation result at the end of the talk. Okay, so this is basically this is the philosophy or the red line in this lecture today. Okay, so part 2, the Landau Hamiltonian with the delta potential. How to define such an operator? Well, we start with the unperturbed thing. So the magnetic gradient you have already seen. I will just abbreviate it by nabla A. So B is a positive constant, and the vector potential is denoted by A. With the magnetic gradient, you have a non-negative closed quadratic form on the first order magnetic Sobolev space H1A. And so this gives rise, defined in a natural way. So this gives rise to a self-adjoint operator, which we will denote by A naught. So this is formally the gradient squared. It's defined on a second order magnetic Sobolev space. Is the operator associated to this form. And well, of course, Landau Hamiltonian is well studied and understood. Typically, you use creation and annihilation operators to analyze it, and you will find out that its spectrum is, well, very much different to non-magnetic Schrödinger operators. It's discrete. No, it's not discrete, but it consists of eigenvalues only, each of them of infinite multiplicity. So the spectrum is just essential spectrum consisting of discrete points. I will put the picture here, although it is probably clear to everybody. So here is the spectrum of the Landau Hamiltonian. Here is B, and here we have 3B and 5B. And maybe I should use the notation of Landau levels. So this is the lowest level, lambda naught. Here is lambda 1, lambda 2, and so on. Well, and each of these levels is an infinite dimensional eigenvalue. So let me put here an infinity, just by indicating geometric multiplicity. Okay. As a remark, the eigenspace corresponding to the lowest level is particularly easily accessible. You can identify the eigenspace with a space of analytic functions. You could call it a Bergmann-Siegel space or maybe Fock space or something like that. This fact here will somehow, it is the reason for that we have better results for the lowest levels than for the higher levels, as you will see later. Okay, so far so good. The Landau Hamiltonian, as you can imagine, comes from physics. Well, at that time papers were written in German. Bemerkungen zur Quantelung des harmonischen Oszillators im Magnetfeld by Fock and Diamagnetismus der Metalle by Landau. These are, of course, physics contributions. It took a while until these magnetic operators were rigorously studied in the math literature. One of the earlier contributions is by Ikebe and Kato from '62. And then I would also like to mention papers by Simon and Kato. And of course, after that, there is an enormous amount and list of publications on magnetic Schrödinger operators. Good. So we want to perturb this Landau Hamiltonian by a delta potential. And probably this is a good point to draw another picture. So we have a curve in the plane. And this is assumed to be the boundary of a C11 domain. So this is omega I for interior. The complement will be denoted by omega E for exterior domain. And their common boundary, this is where the distribution is supported, is this closed curve, which will be denoted by sigma. Good. We shall then approach this maybe first via the quadratic form method. So you take the form for the unperturbed Landau Hamiltonian, this one. I'm mixing it up here all the time. You take this form, and now you perturb by some form on the boundary where this alpha in L infinity coefficient and the traces of the functions appear. The natural form domain here is the first order magnetic Sobolev space, of course. Then it turns out that this form A alpha is a closed semi-bounded form, so it gives rise to a self-adjoint operator. And now very similar to what you saw on the first slide, you see this perturbed operator, its action is actually just as the free Landau Hamiltonian. I'm using here a decomposition notation for the functions. Yeah? So a function f in L2 on the plane will be decomposed in Fi and Fe, which is just the components in the interior and exterior domain. So this is just based on the decomposition of the L2 space in an orthogonal sum of the L2 spaces on the interior and exterior domain. Yeah? This is how it is meant. So this perturbed operator now once again, it acts like the Landau Hamiltonian on functions in the interior and the exterior domain, but then something strange or something special is happening in its domain. So there is a continuity condition, as before, but then the derivatives, and here you now speak of the traces of the normal derivatives, they are not continuous, but there is a jump, and this jump is actually proportional to the trace of the function. Yeah? All traces are understood in the sense of traces for functions from Sobolev spaces. So these transmission conditions here in the two-dimensional case are, let's say, the perfect analog of what you have seen for point interactions before. So let's go back. Still not here. Yes, sorry. Yeah, so you have continuity of the function and you have a jump of the derivatives, which is proportional to the value of the function and the coefficient alpha. So the same thing is appearing in the multidimensional situation, which we have here. Huh? Yes?
It's H22.
I was worrying about this, so I did not want to speak about this space. Huh? So life is not as easy as I'm trying to tell you. So there is a little bit regularity issues of the functions close to this curve. So H3 halves delta A is a magnetic Sobolev space of order 3/2. Yeah? To give you an idea what is going on, if this alpha coefficient would be a bit more smooth, like C1 should do, then you could take here H2. But if the alpha coefficient is just L infinity, you lose a little bit of Sobolev regularity near this curve. In the end, it is not very essential for the results. But to be precise, I put the right space here. Okay. Well, so the notation for this perturbed operator will be just A alpha. The Landau Hamiltonian plus alpha times distribution. Good. When you approach this, there are different ways how you can look at these perturbed operators, and one is via extension theory. What is meant by this is as follows. Our Landau Hamiltonian is self-adjoint in L2, this is clear. Now you could restrict your self-adjoint operator by an additional boundary condition, which is an interface condition. So suppose you take your Landau Hamiltonian and you restrict it to all functions which vanish on this curve. Then you lose a lot of dimensions in the domain, infinitely many, of course. Yeah? So this S actually is a symmetric operator of infinite defect. But then you can also view the perturbed operator, where something is happening along this curve, as an extension of this S. Yeah? So the perturbed operator and of course the original Landau Hamiltonian, they can both be viewed as different self-adjoint extensions of this symmetric operator, which is equivalent to saying that they are both self-adjoint restrictions of the adjoint. So it is like you work with an adjoint and you restrict by boundary or transmission conditions, and then there are tools and techniques from abstract operator theory which can be useful here, and the ones that we are using and we have in mind are so-called boundary triples and the corresponding Titchmarsh-Weil-M functions. So this is somehow a technique from extension theory which enters in our analysis. Yeah? You won't see it in the results, but much of it is behind. So now we go in direction results. So what about spectral properties of these perturbed Landau Hamiltonians? Well, I need a couple of objects that I have to show you. It all is inspired from an explicit resolvent representation of the Landau Hamiltonian. Yeah? So once again, A0 is the free Landau Hamiltonian, and the Green's function or the integral kernel of the resolvent is explicitly known. We just denote it by G lambda. And with the help of this G lambda, I will define certain boundary integral operators, which for traditional reasons I'm calling gamma field and Weil function, but you could also call it a single layer potential or singular layer or hypersingular potential or whatsoever. So what these integral operators do is formally the same as up here, with the little difference that gamma lambda, for example, just takes L2 functions on the curve and maps them to L2 functions on the plane. And if you now take the trace of this gamma lambda, then you have a mapping that maps from L2 on the curve into L2 on the curve. Yeah? Formally, it is these integral operators, and you have to check that they are meaningful, of course. Yeah? But you have natural boundary integral operators which are kind of induced by the resolvent of the unperturbed object. You can give a different interpretation to gamma lambda and m lambda. Gamma, for example, is a kind of Poisson operator, so it solves the PDE. You plug in phi, then gamma lambda phi will be a solution of this eigenvalue problem. The solution is continuous along the curve, and the derivative has a jump which is just equal to the phi that you plugged in. And in the same manner, the M is something like a Neumann to Dirichlet map. So the M does the following. It takes basically, it takes basically these jump values of the derivative and maps them to the trace of the solution. Something like Neumann is not exactly very precise, but something like jump or difference Neumann to Dirichlet, something like that. Yeah? So these objects are meaningful and they will now appear naturally in the analysis. Okay, so now we finally come to some results. So the first thing is that as long as you are in the resolvent set of the free Landau Hamiltonian, so you are outside of the Landau levels, then actually you have an abstract type of Behrmann-Schwinger principle. So you get eigenvalues of your perturbed Landau or your perturbed operator by analyzing actually this Weil function. Next is you get an explicit representation for the resolvent of the perturbed operator. So once again, here is the resolvent of Landau, this object you know well. Here is the resolvent of your perturbed operator, which you want to study now further on. And here is how the two differ. And this term here is actually a term that more or less acts on the surface or on the curve. Yeah? In particular, the inner term, 1 plus alpha m lambda inverse, this is an operator that is acting in the L2 space on the curve. And the Behrmann-Schwinger principle above already suggests the spectral data of your perturbed operator is basically hidden in this nonlinear term here. Yeah? And this is what we are going to analyze later on. The first thing you can read off easily is there is a compactness or a Schattenclass property by just looking at this boundary term and embeddings of Sobolev spaces. So it turns out that this perturbation here is in a Schatten von Neumann ideal for any p larger than 1/3. Yeah? Once again, this is due to embeddings of Sobolev spaces. So it's trace class, it's Hilbert-Schmidt, in particular it's compact, so certainly essential spectrum is preserved. So this is a compact perturbation, essential spectrum of your perturbed operator will be the same as of our Landau Hamiltonian, and so we know what the situation is for the essential spectrum. So I put here alpha now, and we certainly know that these points will remain and belong to the essential spectrum. But what happens around? This is the first most natural question, of course. Yeah? You perturb compactly, essential spectrum is preserved. So what happens with discrete spectrum in the gaps? Yeah? So after the perturbation, you may expect an eigenvalue here, and one is here, and one is here. These are all finite dimensional eigenvalues. But they may, of course, accumulate to the essential spectrum. Same here from the right. So the question is, does this appear? Will it necessarily appear? Can one exclude it? For classical potentials, this answer was probably given by one of Georgi's best known results. Yeah? So in a paper by 1990 in Communications PDE, he actually proved for classical potential, so I mean function, LP, which has definite sign, that this accumulation is actually present, yeah, from above or from below, depending on the sign. This was taken then for many, many more cases, exterior domains, half planes, strips with different boundary conditions, and many of the people who have contributed in this field in the 2D case are here, and this list is of course incomplete, but at least I tried to sum up those papers I knew. It went on, also in connection with the spectral shift function, to the 3-dimensional case, and also there is a bunch of papers in this direction. Okay. Well, what do we obtain for singular perturbation? This is the topic of this next slide here. Well, essential spectrum, as you see, is Landau levels, B, 3B, 5B, and so on. And now it comes to a sign condition in the perturbation. The first result is kind of clear. You see, if the alpha in the perturbation is non-negative, then you do not expect eigenvalues from below. Yeah? So it is clear that when alpha is non-negative, or more or less clear, that there is no accumulation from below. This is no surprise. What is less clear, but remains true, is if the alpha is positive, then indeed there is accumulation. So this picture that was indicated here is really appearing. So the Landau level under this singular perturbation kind of splits or smears out and leads to accumulation of discrete eigenvalues, well, from the right, if your perturbation is positive. And I mentioned in the very beginning, life is always a little bit better at the lowest level. You see, so for the lowest level, it suffices to assume that alpha is non-negative and not vanishing on the whole curve to already observe accumulation from the right. Okay, you can flip signs and then you generate the same results from the other direction. Yeah? Of course, if alpha is negative, then things go upside down. And so why is this the case? How you approach this, let's say? You look at this resolvent formula and the perturbation term. So the perturbation term is here. And now you compress the perturbation term onto the eigenspace of the Landau level. And now you do analysis and check that this is an infinite rank operator. And if you succeed, it leads via, let's say, standard spectral techniques to accumulation of eigenvalues. Okay, so this is first result. Next one is a bit more precise, but also a bit more special in the sense that I need to assume a bit more smoothness for the curve. I think the curve so far was C11. Yeah? Now I would like to have it C infinity smooth. If it's C infinity smooth, alpha positive, then for sure you have accumulation, but you even have spectral asymptotics. And these asymptotics here can be described in terms of the capacity of the curve. Same thing if you flip sign, of course. And so what is that? Well, the capacity is here the so-called logarithmic capacity. It's a notion from potential theory. So what you do is actually you take the supremum, which then turns out to be a maximum of e to the minus logarithmic energies, where you take the supremum over all compactly, over all measures, probability measures supported on this curve. Okay, one further. Here we have assumed alpha to be positive on the full curve. If you just have it on a sub-arc, then basically the result remains the same, where now the capacity of the sub-arc appears. And again, same thing if you flip signs. And so where does that come from? Well, this is heavily inspired by analysis of Toeplitz-type operators, which we rely on, and where the corresponding results can be found in the paper by Puschnitsky and Rosenblum. Yeah? So that is, in a way, a reduction to their results, which then implies our spectral asymptotics, via asymptotics for Toeplitz operators. So we move ahead. This is where now Georgi came into play. When you look at this picture once more, then we have some principal understanding about accumulation and non-accumulation to Landau levels. But of course, the next natural question is, what happens with the level itself? So it used to be an infinite dimensional eigenvalue for the unperturbed operator. After the perturbation, you just know that it's in the essential spectrum. So it may be in the continuous spectrum and being just an accumulation point of discrete eigenvalues, or it may remain an eigenvalue. Maybe it's a finite dimensional eigenvalue, it may also be infinite dimensional. We don't know. Huh? And so this is what is meant by fate of Landau levels. What happens with the level? Life is good with the lowest level, which is gone as an eigenvalue, and hence remains a point in the continuous spectrum. For the higher order levels, life is not so clear. This is more like an observation. You see, if your curve happens to be contained in a zero set of an eigenfunction of the unperturbed Landau, then naturally this eigenfunction also satisfies your transmission conditions, and so it may very well happen, depending on the choice of your curve, that actually the Landau level is preserved as an eigenvalue. And this is interesting to remark because it's very different to what happens in the classical case. And here I'm referring to a paper by Georgi and Frederick Klopp from 2009, which is named Fate of Landau Levels, because what they actually prove is that the levels disappear as eigenvalues if you perturb by classical potentials. So take the free Landau Hamiltonian and perturb it by a sign-definite potential V. The V shouldn't be too big because otherwise it influences the next highest level, which we are not interested in. So if you perturb by a sign-definite V, then actually the level disappears as an eigenvalue. For singular perturbations, this is in general different. And you can actually analyze situations where more can be said. So if, for example, this loop sigma is a circle with positive radius r, and let's say our interaction strength for simplicity is just a positive constant, then first of all eigenspaces, all Landau levels can be at most finite dimensional, and one can show that there are many, many Landau levels which actually survive during this singular perturbation, or which survives the singular perturbation, in the sense that they remain eigenvalues, but they will become finite dimensional. So what happens is your infinite dimensional isolated eigenvalue of your Landau Hamiltonian is transformed into something finite dimensional, and infinitely many discrete eigenvalues accumulating to this level from the right or from the left, depending on the sign of your perturbation. Okay, so last result I want to show you is a kind of justification for our models. This is now approximation. So in which sense do these model operators can be viewed as real-life Hamiltonians? Well, suppose you have an L infinity function V, so a classical potential, and for simplicity it is just supported in a tubular neighborhood of your curve sigma. Then you start to scale it. And by scaling it, I mean what is explained up here. So, well, you shrink your tubular neighborhoods, or you shrink the support of your V by pushing it together and increasing the values by scaling them by 1 over epsilon. Outside of this tubular neighborhood, you set it 0. Each V epsilon, for epsilon positive, still remains, of course, to be an L infinity function. So you can define the classical Hamiltonians just by, this is a bounded perturbation actually for epsilon positive. So you perturb the Landau Hamiltonian just in a traditional way by adding a bounded potential. These will be self-adjoint operators on the second order magnetic Sobolev space. And then one can show that actually you have the following estimate or convergence. So these classical perturbed Landau Hamiltonians converge to a singular perturbed Landau Hamiltonian in this form when epsilon tends to 0, and the alpha coefficient that is kind of measuring the strength of the interaction can be read off by integrating this potential V perpendicular to the points on the curve. So the alpha you can compute out of the V. And you can also do it the other way around. If you start with an alpha, you find a family of V's where this convergence actually takes place. Okay, so you have convergence in the norm-resolvent sense, and this is of course very appropriate and convenient for spectral analysis because it leads to convergence of spectra, eigenspaces, spectral function, and so on and so on. Okay, so this can be seen as a justification of Landau Hamiltonians with singular perturbations for replacements of Landau Hamiltonians with strongly localized potentials. Okay, thank you very much for your attention.